Today, we are cracking open a secret weapon that scientists and engineers have been using for over a century. It's called the Buckingham pi theorem, and it's this amazing method for taking a chaotic mess of variables, things like speed, density, size, you name it, and boiling it all down to just a handful of key relationships. It's all about finding this beautiful simplicity right in the middle of chaos. So let's dive right in.
To really get why this theorem is such a game changer, let's start with a problem. A classic physics challenge that, honestly, without our little secret weapon, would be completely impossible to solve with experiments alone. It's what you'd call a data nightmare.
Okay, so imagine you're an engineer, and your job is to figure out the drag force on a sphere. Now, this could be anything, right? A ball bearing sinking in oil, a raindrop falling through the sky, whatever. How would you even start to figure that out? Well, you'd have to run some tests, some experiments. But what do you test?
Well, as it turns out, a whole lot of things matter. You've got the velocity of the fluid, its density, its viscosity, that's kind of like its thickness, and of course the diameter of the sphere itself. And then there's the drag force we're trying to measure. That's 5 different variables. If you wanted to test every single possible combination of these, you'd need a practically infinite number of experiments. It's an impossible task. Or is it?
This is where we find our secret key. See, instead of looking at each variable all by itself, the real trick is to find the fundamental relationships between them. The key, it turns out, is in creating what we call dimensionless numbers.
And this slide, this slide has the perfect analogy to make it all click. Think about a recipe for a cake. You could write down the exact grams, 200 grams of flour, 100 grams of sugar. But that recipe only works for one specific cake size. A much more powerful, much smarter recipe uses ratios, 2 parts flour to 1 part sugar. And suddenly, that relationship, that ratio, is universal. It lets you scale the recipe for a tiny little cupcake or a gigantic wedding cake. Dimensionless numbers do the exact same thing for physics. The big idea here is that the relationship between variables is so often way more important than their individual values.
So, our mission, if we choose to accept it, is to stop thinking about 5 separate variables and instead discover the fundamental ratios, these powerful groups that really govern the drag on a sphere. We want to find that universal recipe that works for any fluid, at any velocity, with any size sphere.
And the tool we're going to use to systematically find these special groups is the Buckingham pi theorem. It gives us a really clear 5-step process to basically crack the code of any physical system. Let's walk through exactly how it works.
So here's the game plan, the 5-step roadmap. It's super logical. We'll count up our variables, pick a few building block variables, identify the fundamental dimensions like mass, length, and time, do one super quick calculation, and then we assemble our final groups.
Step 1, easy. It's just a simple count. Like we just saw, we've got 5 variables in play: force, velocity, density, viscosity, and diameter. So our variable count, which we call k, is 5. Simple as that. Step 1 done.
Okay, step 2, which isn't on this slide, involves choosing what we call repeating variables. Think of them as the core building blocks for our dimensionless groups. For our problem, we'd pick density, velocity, and diameter. Now that brings us to step 3. We identify the fundamental dimensions involved. Every single one of our variables is just some combination of mass, length, and time. That's it. So our dimension count, which we call R, is 3.
And this is where the magic really happens. Step 4 is just simple subtraction. The number of powerful dimensionless groups we need is k minus r. So 5 variables minus 3 dimensions equals 2. That's it. That entire infinitely complex problem just collapses down into finding just 2 master groups. And by the way, why are they called pi terms? It's not about the number 3.14. It's just because the Greek letter pi is traditionally used as a symbol for these amazing dimensionless groups.
So how do we actually find them? Well, step 5 is basically a puzzle. We combine our variables and we raise them to certain powers, those little a, b, and c exponents you see there. The whole goal is to choose those exponents so that all the units, kilograms, meters, seconds, all of them completely cancel each other out, leaving us with a pure, perfect, dimensionless number.
Okay, we've followed the method, we've solved the puzzle, so what did we find? What are the 2 master groups that describe all the physics of drag on a sphere? This is the big payoff.
Our first pi term is one of the most famous and important numbers in all of fluid dynamics, the Reynolds number.
You can see it combines 4 of our original variables, density, velocity, diameter, and viscosity, all into a single powerful value that tells you everything about the character of the fluid flow.
And our second pi term is the coefficient of drag. This is the other half of the puzzle. This is the group that contains that last variable we were looking for, the force we wanted to measure in the first place. It basically quantifies the slipperiness of the object as it moves through the fluid.
So what's the big takeaway? The crucial insight? It's this profound statement right here. That entire universe of possibilities, every fluid, every speed, every size, it all collapses into a single clean relationship. This hugely complex physical problem is governed by one fundamental ratio, not a messy pile of individual variables. If you know the Reynolds number, you can predict the coefficient of drag. It is that simple and that powerful.
Now you might be thinking, okay, that's a cool math trick for a sphere, but this isn't just a neat trick. This principle of finding these dimensionless relationships is a cornerstone of modern science and engineering. It lets us solve problems that would otherwise be completely, totally unsolvable.
And I mean, this isn't just theory. This stuff is the bedrock of how we build the modern world. Think about it. How do you test a new airplane design without building a full-size plane? You build a small model. This theorem is the mathematical guarantee that lets engineers test that little model in a wind tunnel and know, with certainty, how the real thing is going to fly. It's used to design the sleek hulls of ships to cut through the water. It even helps bioengineers develop artificial heart valves that mimic the flow of blood perfectly. It is the essential tool for taking a complex reality and finding the simple, scalable rules that run the whole show.
The Buckingham pi theorem really teaches us a powerful way of thinking, to look past all the surface-level variables and search for the fundamental ratios, the deep relationships that truly define a system. And it leaves us with this really fascinating question. What other seemingly impossible problems out there are just waiting for us to find their hidden simplicity?